Hey everyone, Land Assistant here, and based on popular demand, I am happy to begin our series on differential equation. So what is a differential equation? A differential equation is simply an equation containing an unknown function and its derivative. An example of a differential equation is dy over dx is equal to x squared. Here, the derivative is dy over dx, and the unknown function that gives this derivative is this y, or y of x. We know the derivative, and we are solving for the function that gives that derivative. And the process of solving for that unknown function is called as solving the differential equation. Differential equation has a lot of applications in real-life situations because oftentimes we know the change because they are observable change, and we do not know the function that caused that change. An example of that would be this rocket. We can observe that the change in mass with respect to the change in time is equal to -8 times t, where t is the time in seconds and it is greater than or equal to 0. If we want to find the function m of t given this scenario, then we are solving a differential equation. But before we go to more serious applications like this, let's build our skill first by learning different techniques of solving differential equations. And in this first video in the series, we are going to talk first about solving differential equations by direct integration. This is the technique that is applicable when the given differential equation is in the form you have the derivative and you have a function of x at the right side. In other words, you do not see a combination of the variable y or the variable x at the right side of the equation. And if the integral equation looks like this, then we say that that is a directly integrable differential equation. And the process of solving this directly integrable differential equation is simply by integrating both sides of the equation. So if we integrate the left side, we now have the antiderivative of dy over dx, and we also find the antiderivative of the right side, so the integral of f of x dx. Now, since finding the derivative and finding its antiderivative are inverse operations that cancel each other out, then this left side will result to the function itself, and the right side is the antiderivative of f of x dx. And if it happens that this right side can easily be integrated, then solving differential equations by direct integration this way is the simplest method of solving differential equations. Let's have an example. Let's say we have dy over dx is equal to x squared. Using now direct integration to solve this differential equation, then we find the antiderivative of both sides. Then this left side is simply equal to y. For the right side, the antiderivative of x squared dx is x to the 2 plus 1 over the same exponent 2 plus 1 plus an arbitrary constant c. This is using the power rule of anti-differentiation. Simplifying, this is equal to y equals x to the third over 3 plus c. Just like that, we already know what is the function y of x that causes the observed derivative of dy over dx equals x squared. Now, to check if our answer is correct, then we can just reverse the process. So from the result y is equal to x cubed over 3 plus c, we take the derivative of both sides. So we have dy over dx equals the derivative with respect to x of x cubed over 3 plus c. And this is equal to dy over dx equals the derivative of x cubed over 3 is 3x squared over 3 plus the derivative of a constant is 0, and 3 divided by 3 is equal to 1. So we arrive at dy over dx is equal to x squared, which is the original given equation. So to summarize now the process, this method is applicable when the given differential equation is directly integrable, and to solve this, we take the antiderivative of both sides of the equation, and since differentiation and integration are inverse operations that cancel each other out, the left side is simply the function y of x, or y, and the right side is equal to the antiderivative of x squared dx. The right side now is equal to x cubed over 3 plus c. Here, c is an arbitrary constant, meaning you can have so many different equations that is solution to this differential equation depending on the value of c. So generally, we now call this as our general solution to this differential equation, solved using direct integration. And we can do the checking by reversing the operation. And here is the result that gives us the general solution to this differential equation. So the general solution is y equals x cubed over 3 plus c. Now for the particular solution, if we know the initial condition, let's say if we know that y equals 3 when x equals 2, then we can compute for the particular solution by just substituting y equals 3 and x equals 2 to the general solution, and then solve for c. So we replace y by 3, we replace x by 2. Solving now for c, we multiply both sides of the equation by 3 to arrive at 9 equals 8 plus 3c, and finally c is equal to 1/3. So the particular solution of this differential equation dy over dx equals x squared when the initial condition is y equals 3 when x equals 2 is y equals x cubed over 3 plus 1/3. So this is the function that will give us a derivative of dy over dx equals x squared given this initial condition. So that's the main concept behind differential equation. A differential equation is simply an equation containing derivatives and some unknown functions that resulted to that derivative, and our goal is to find that unknown function. So here we are not just solving for any particular value, we are solving for the function itself. And that's make it different than the regular equations that you are solving in algebra. For your homework, here is the problem. dy over dx is equal to e raised to 2x. Find the function y of x that gives this derivative. So thank you very much, and we'll see you again in our next video in this series, Solving Differential Equations.